Module 3. And in this module, we're going to be talking a lot about water. So this module is all about water. Not just when water is falling from the sky, but the fact that water is actually in the air around you right now. So the first thing we're going to talk about is how this water actually affects the temperature around you. And then we're going to talk a little bit about what's called the water cycle. So the goals for this lecture are first to understand what latent heat is and how latent heat is exchanged with the atmosphere during a phase change. Then in the next module, in the next lecture, we're going to talk about condensation, evaporation, and saturation. And then we're going to talk about relative humidity and dew point. So, first off, what if I were to tell you that we are surrounded by water? Well, the fact of the matter is that's true. Approximately 0 to 4% of our atmosphere's air molecules at a given time are water. So right now, you are actually in a room surrounded by water. Now with that said, there are times when there's a lot of water in the air, and we usually call those very humid days, and then other times where the air is relatively dry and there's not a whole lot of water in the air. However, if you've ever had a bad hair day, like I did back in 2006, man, look at those curls. A lot of times that bad hair day is related to the fact that there's a lot of water in the air. Have you also wondered why humid days are worse than dry days? And this is something that you might not experience if you only are here on the West Coast, but if you actually fly over to the East Coast to cities like Washington, D.C., Miami, Florida, New Orleans, Louisiana, or any area in the Deep South, not only is it hot during the summer, but there's a lot of moisture, a lot of water in the air, and so it actually also becomes very muggy, very miserable. The heat, it just feels so much worse. Well, we're going to talk about why that happens today. So, first off, one thing I think we take for granted, but is very, very important, is that our Earth is unique. We live on this gigantic planet filled with lots of water. And that's very unique compared to most of the other planets in the solar system and all the other planets in the solar system. Now, with that said, we have found evidence for water on Mars. We found evidence for water on other planets and water in outer space. But what's so unique about Earth? Well, Earth is unique because of our temperature range. The temperature range here on Earth is approximately minus 130 degrees Fahrenheit to positive 130 degrees Fahrenheit. A little bit give or take. But this temperature range actually allows us to have water on Earth in all different phases. And when I say phases, I'm talking about solid water, that's ice, liquid water, that's water droplets, rain, cloud droplets, and then gas, that's water vapor. And so water is actually present on Earth, readily present, naturally present in all three of these phases. And that is crucial to sustaining life on Earth. Now today we're going to be focusing mainly on liquid water and water vapor. We'll talk a little bit about solid water, talk a little bit about ice, but we're mainly going to be focusing on liquid water and water vapor. So, one of the things about water on Earth is not only is water readily available in all three phases, but those phases actually are constantly changing. Water is regularly changing phases, and that means it's transitioning from one phase to another. So water is constantly evaporating, or water is constantly condensing, or in some cases if the temperature is low enough, water is constantly freezing, or water is constantly melting. but water is constantly changing phases. And the phases that we're pretty well familiar with are evaporation. I mean, if you've ever seen steam coming off of a boiling pot of water, a lot of that water is evaporating. Condensation, if you've ever been outside on a humid day and you had a glass of ice water and it looked like the glass was sweating, that's condensation. And then obviously freezing and melting. So we've experienced all of these phase changes, and we see them in our everyday life. But there's one thing that we really take for granted, and yet our bodies actually naturally know it. So even if you don't understand it, your body actually gets it. And that is the important concept of what's called latent heat. So here's what's happening. The temperature of water, if you remember from the previous module, is determined by how fast those molecules are moving. Well, in order for water molecules to move faster, they require more energy. But an interesting fact is not only does water require a certain amount of energy to go a certain speed, those molecules, but water also requires a certain amount of energy to maintain its phase. So there's a certain amount of energy that water absorbs. In order for it to evaporate. Or a certain amount of energy that water absorbs in order for it to melt. And we call this heat latent heat. And the reason why we call it latent heat is that it's heat that actually doesn't change the temperature of the water. The only thing it changes is the phase of the water. And this actually brings us to a pretty interesting fact. If you had a glass of water and you had ice in it, and you left it out, you stirred it up, and you put your thermometer in it, the temperature of this ice water would be 32 degrees. What this means is that liquid, that's the liquid water, and solid, that's the ice, both exist at the same temperature. Now what will happen is if you leave it out at room temperature, we know that heat transfers from warm object to cold object, so over time heat is going to be absorbed by the glass of water, and you would think that the temperature would increase. But actually leave the water out, let it sit out for 10 minutes, let it absorb that heat, give it a stir, and as long as there's as long as there's still ice in the glass, the water's temperature will remain at 32 degrees Fahrenheit. And the reason why is because any heat that's being absorbed by the water isn't going to raise its temperature, it's going to melt the ice. What will eventually happen is all the ice will melt, and then the temperature of the water will begin to rise. So basically what happens is if you have ice and you apply heat to it, its temperature rises until it reaches 32 degrees. That is that melting point, or 0 degrees Celsius. Once it reaches that, any heat that's absorbed goes towards melting the ice. Rather than heating it up, rather than adding its temperature, or rather than warming its temperature, it goes towards melting ice. Then once all the ice is melted and it's liquid water, then the temperature begins to rise again until it hits the boiling point. And then any additional heat you apply goes towards evaporating the water. So you could do the same thing with a boiling pot of water. Heat it up to boiling, take the temperature will never be higher than 100 degrees Celsius or 212 degrees Fahrenheit. As a result, latent heat is what's called a hidden heat. Now, what does this actually mean for our atmosphere? Well, believe it or not, it actually means a lot. And there's some pretty important implications and some pretty cool stuff too, related to latent heat. So let's talk about it. First off, when this happens, it can actually affect the temperature of the atmosphere. It can actually affect the temperature of the atmosphere. For example, let's say you have, well, I'll just use the classical example. Let's say you have sweat on your body. You have sweat on your body, and we'll talk about that more in a second. Well, sweat are beads of liquid water. What actually happens, though, is eventually those beads evaporate. Well, in order for them to evaporate, they need to absorb a certain amount of heat. Well, where are they going to get that heat from? They're going to get that heat from their surroundings. So they absorb the heat from the surrounding atmosphere. That causes the atmosphere to cool. And the same thing, or the opposite is true, though, for when water condenses. If you have water that's condensing onto a surface, it's actually releasing heat into the atmosphere. Well, what I want you to know is when water melts or boils, that's called moving up a phase. It has to absorb heat from its surroundings. On the other hand, when water condenses or freezes, I call that moving down a phase. It's going from a higher phase to a lower phase. It releases heat. It releases heat. It releases heat. So here's why we sweat. Believe it or not, sweating is your body's method of cooling itself. And the way that it works is when your body temperature is warm, your body then begins to sweat. It begins to excrete water. And what the idea is that when that water is then evaporated by the atmosphere, it has to suck in heat, thus cooling your body down. It heats the water up, but it cools your body down. What's interesting, though, is the higher the humidity in the atmosphere, the less evaporation can occur. If you've ever been in the Deep South before, if you've ever been in a really humid climate, one of the things that you may notice is that you'll sweat and the sweat won't evaporate. It'll just stick on your body. And that feels really miserable. That's not something that you want to experience, but we experience it all the time. So let me just take a moment and just sort of review this idea real quick. So when water moves up a phase, so it goes from ice to liquid or from liquid to vapor, it has to absorb water from its surroundings. It has to absorb heat from its surroundings. Forgive me there. It has to absorb heat from its surroundings. Well, this means it's taking heat away from its surroundings, thus cooling those surroundings. So when water evaporates, it's actually cooling the atmosphere. Again, that's why we sweat. If you've ever gone to a swimming pool before and gotten out of the swimming pool, even on a hot day, you'll start to feel cold, especially if it's windy outside. Why? Because evaporation is happening and that's cooling your body down. Now, on the other hand, moving down a phase, going from vapor to liquid or from liquid to ice, that actually releases heat into the atmosphere, warming the atmosphere up. Warming the atmosphere up. Now, with that said, there's one more thing I want to talk about. There's also a fourth type of phase change. Actually, a third type of phase change, I lied. Sorry. There's a third type of phase change. So, when talking about ice going from solid to liquid to gas, it's actually possible to skip the middleman and go simply from ice to gas. We call that sublimation. And it works the same way as moving up any phase. In this case, it has to absorb heat from the surroundings, cooling the surroundings. On the other hand, you can go from vapor straight to ice by skipping the liquid phase. This is called deposition. And we're actually going to talk a little bit about this in the next module when we talk about what's called the Bergeron process. And again, in this case, heat has to be released from the water in order for it to sublimate, in order for it to deposit, in order for it to stick to ice crystals. Now, one of the things that is a common pitfall, a common area of confusion, is when I say evaporation is a cooling process, or evaporation cools the atmosphere, or condensation warms up the atmosphere. Well, something that a lot of people get confused by is they think, well, wait a second, don't you have to heat water up in order for it to evaporate? How is that a cooling process? Well, the reason why it is because we're not actually talking about the water. We're actually talking about the atmosphere. So yes, the water, when evaporation is occurring, yes, the water is heating up. But that heat's got to come from somewhere. And that somewhere is the surrounding atmosphere. And since heat is being taken away from the surrounding atmosphere, that causes it to cool. That causes the atmosphere to cool. So when we say evaporation is a cooling process, we're talking about from the atmosphere's perspective. Not from the water's perspective, from the atmosphere's perspective. And the same is true when we talk about condensation. When condensation occurs, there's a certain amount of latent heat that was in that water that is then released into the atmosphere. And so condensation actually warms the atmosphere up. Now, why does this even matter? So I've already mentioned that our bodies know that latent heat helps cool us down because if we sweat, the sweat absorbs that heat and that cools our bodies down. But how does this actually relate to meteorology? How does this relate to weather? Well, the reason why it relates to weather is because this means that water is an energy reserve. There's a lot of energy that's just present in water when it's in that water vapor phase. And as air rises into the atmosphere, any water in that air can condense. And as it condenses, it releases that heat into the atmosphere. That provides energy to the atmosphere. And that energy can then fuel storm systems. And in fact, some of the stormiest weather takes place in some of the most humid climates. If you're like me and you live in California, you realize that we don't get a lot of stormy weather here. We don't get hurricanes here. We don't really get thunderstorms here. When it rains, it's usually in the wintertime and it's usually not that bad. Well, the reason why is because it's not very humid here. However, if you live on the east coast of the United States, they get hurricanes, they get thunderstorms often. It's because there's a lot of moisture there. And because there's a lot of moisture there, there's a lot of energy. Now we're going to talk more about this idea in the next module when we talk about what's called adiabatic cooling. And what you'll actually discover is that when there's a lot of moisture in the air, that slows down the rate at which air cools. That allows air to rise higher, that actually allows thunderclouds to develop. So we'll actually talk about that in the next module. Another example I'll give are hurricanes. So I've already mentioned storm systems, and I mentioned hurricanes briefly, but hurricanes need a lot of moisture in order for them to grow. And actually, as I'm recording this lecture right now, there's a hurricane out in the Pacific Ocean that has just crossed over into a drier environment, and it's quickly weakening. That's very common for hurricanes. When they leave an area of tremendous heat and moisture, they fall apart. Well, what actually happens is when you have a hurricane and it's traveling over warm ocean waters of at least 78 degrees Fahrenheit, they absorb that heat, and that causes them to grow in intensity. On the other hand, when a hurricane is not near warm water, when it's either traveling over land or over cooler waters, it rapidly weakens. It rapidly weakens. Now, a good example of this whole process is Hurricane Katrina. So, Hurricane Katrina, if you don't remember, was actually one of the most intense hurricanes in history. Actually, the maximum sustained winds at one point were 175 miles per hour. Now, by the time it hit Louisiana, it wasn't that intense. However, it was still pretty bad. Well, what actually happened is Katrina moved over a patch of very warm water. And it basically slurped it up the same way that you would slurp up soup. And so it received all of this moisture. As that moisture rose into the atmosphere, it condensed, releasing that heat into the storm, allowing the storm to intensify. What was left behind after Hurricane Katrina slurped up all of this warm water was cooler water behind it. And this is a process called upwelling. We're going to talk more about upwelling in a few weeks when we talk about global circulation. But for now, just know that as this hurricane traveled over this water, it basically slurped it up. And the heat that was present in that water, when it condensed, was released, strengthening the storm. So that's why latent heat is so important. Latent heat is important because it acts as fuel for weather systems. And again, it also acts to cool our bodies down when we're hot. So the next time you're sweating, remember, that's just your body trying to cool itself. And if the sweat isn't evaporating, it's because there's a lot of humidity already in the air. Now, next time we're going to talk about what happens when there's as much humidity in the air as can be possible. And we're going to talk about something called saturation.